Thanks for watching. This is our final video in the unit, and the topic is called interference of sound waves. I think you're going to enjoy this one. It's not very mathematical, but it's actually quite an important topic in physics. And so let's get right into it with a quick checkup on where we are. In the homework schedule, it's lesson 9. The section in the textbook is 7.4. We're going to be looking at something called interference of sound waves, two different kinds, if you will. One is called beats, and one is called two-point interference, and I'll explain both of those in a minute. Make sure that after you watch this video, you take some notes on the section and look at some of the sample problems, and then in class you'll have an opportunity to try some of the questions as well as some at home. I'm going to do some demos, so make sure you come to class. And one last thing, make sure if you are someone who finds this useful that you check out the learning goals, so you have a checklist of what we're learning, and the success criteria, a checklist of things that you should be able to do by the end of this lesson. All right, without any further introduction, let's get started. First thing I'd like you to do is think back to those tuning forks that we had in class. Now, these are photos that I've taken from YouTube, but I think they'll get the idea across. Imagine there are two tuning forks that are being played, and for argument's sake, let's imagine that one of them is set to ring at a frequency of 10 hertz, and the other one is set to ring at a frequency of 15 hertz. Now, since there are two frequencies and we don't want to get confused, we'll call one of them F1 and the other F2. Now, some of you might be thinking, hey, whoa, wait a minute, stop. A frequency of 10 hertz is not audible to the human ears. Why are you suggesting that a tuning fork would ever ring at that frequency? And if that's what you thought, then congratulations for thinking critically. The answer to the question of why I picked these numbers is because it's going to make the argument that I'm about to propose to you a little bit easier to understand. Okay? So anyway, allowing me to do that, let's imagine what would happen if both of these were ringing at the same time. And if you're wondering what's an application in real life where you might encounter this, imagine two singers who are trying to sing the same note, but one of them is a little bit off. You know, maybe the correct frequency is this, 10 hertz, but the other one is off by 5 hertz. I'm sure you've heard people try to sing together and something sounds awful because one of them is out of tune. Or perhaps you play the guitar or violin and you can imagine trying to tune two strings. You try to make them sound the same when you're tuning them. When they don't sound the same, well, it's kind of like these two tuning forks, which are slightly off. Or maybe you play in a band and you're tuning at the beginning. The guitar, the piano, and the bass are all trying to tune so that they can play together very well. When they sound out of tune, something's definitely wrong. So that's your application. Now, what's going to happen when we ring these two tuning forks? Well, keep in mind, the heads of the tuning fork, they vibrate back and forth like this when you strike them. And in doing so, they send out compressions of sound waves in either direction. And that is what we call compressions and rarefactions, if you recall. Compressions, rarefactions, etc. And as those get created, of course, they're being created by both of the tuning forks, and they're going to overlap in whatever room that we happen to be playing these. So this diagram here, which is also from your textbook, Physics 11 by Addison Wesley, you see for the 10 hertz tuning fork and the 15 hertz tuning fork, remember this means 10 cycles per second, or 10 vibrations per second. So what they've shown you down here is 1 second worth of time, and they're showing you how the compressions would be spread out in time. So for example, the first one at time 0, and then another one at a 10th of a second, a 20th of a second, a 30th, and so on. That would be 10 100ths of a second, 20 100ths of a second, 30 100ths of a second, my apology, 0.1, 0.2, 0.3 of a second. You see them being produced, a grand total of 10 in 1 second if we don't count the first one at 0. Now let's look at what the 15 hertz tuning fork would be doing. It's going to create 15 compressions in 1 second, evenly spaced in time, And so if you take 1 second and divide it into 15 parts, you'll notice that after 1, 2, 3, 4, 5, 6, these are the times that those compressions are landing on. So make sure that you understand how these 15 compressions land on the different times here. What you're going to notice is that every so often, a compression from the 10 Hertz tuning fork and the 15 Hertz tuning fork, they overlap. And when they overlap, your textbook has drawn you a line in the middle here. Now they're out of phase. You can see that this compression does not match up with any of the others, but a short time later, they overlap yet again. And this continues overlapping at regular intervals over the 1 second of time that we are imagining here. Now, count them. 1, 2, 3, 4. There are 5 overlaps. 5 overlaps every second. Now think to yourself, what would happen if the compression from one tuning fork overlapped with the compression of another? Well, they would interfere constructively. And in sound waves, that would indicate a louder sound than you are used to hearing. In other words, 5 times every second, you're going to hear something that's sort of extra loud. And we have a name for this. We call it a beat. In class tomorrow, I'm going to show you guys what a beat sounds like. But if you are a guitar player or a violin player, or if you've ever played in a band where you took time to tune your instruments, you might have noticed that when any two people are trying to play the same note, but they are slightly out of tune, you hear this sort of fluttering sound, sort of a wah, 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 wah sound. And those are called beats. They are the indication that two sound wave sources have slightly different frequencies, and due to constructive interference, every now and then their compressions overlap and create that loudness, which we call a beat. Now, if there's 5 beats per second when a 10 and a 15 Hertz tuning fork ring, can you guess what the formula is to calculate the beat frequency? Well, it should be pretty clear to you that if you do F2 minus F1, that's 15 minus 10, you're going to get the 5. But you'd also get a 5 if you did F1 minus F2, then you'd get 10 minus 15. Well, I guess that would be negative 5. So that's almost correct. It's the right number anyway, just negative. So what your book does is they just place these in absolute values so that we never have to worry about whether we have a negative sign. Absolute value of F1 minus F2 is equal to what we call the beat frequency. Now let's look at an application that uses this. It says here, when a tuning fork of unknown frequency is sounded simultaneously with a 512 Hertz tuning fork, so maybe we could call this F1, and we could call that F2. It says 20 beats are heard in 4 seconds. Now make a connection here between something you learned a long time ago and something that you need to know now. 20 beats in 4 seconds, that's telling you the beat frequency. Remember the letter N for the number and delta T for the time. So we've got 20 beats in 4 seconds, giving us a beat frequency of 5.0 Hertz. So now, the previous information is telling you that when sounded against a 512 Hertz tuning fork, you get 5 beats. What are the possible frequencies that could result in this? Well, 512 plus 5 equal to 517. These two frequencies of tuning forks would give you the 5 Hertz beat frequency. But then again, so would 512 minus 5 equal to 507. These two frequencies, 507 and 512, would also give you 5 beats. The positive or the negative doesn't matter, and that's where the absolute value sign in the equation comes into play. So whether you want to go solving an absolute value equation mathematically, or you just want to reason it out using a little bit of logic, is up to you. But realize that the known frequency plus or minus the beat frequency gives you the other unknown frequency. Now here's a little bit of a challenge for you. How could you actually figure out what frequency the unknown tuning fork had? Well, think about it for a minute. If the actual frequency were 517, would this tuning fork sound any different than the 512 Hertz tuning fork? Sure it would. It would have a higher frequency, it would have a higher pitch, so it would be kind of higher rather than lower. However, if the frequency was 507, it would sound lower rather than higher, like that. There's my lousy attempt at singing tuning fork frequencies for you. All right, so sometimes just by listening, we can tell which frequency of the two is involved. Sometimes the frequencies are so close together, it's really hard to tell whether you're dealing with the higher one or the lower one. In that case, what you can do is what guitar players do when they're tuning their strings. You take the unknown tuning fork and you gradually increase its frequency. Why do you increase its frequency? Well, think about it this way. If the unknown frequency is 517 and you gradually raise it up, it will get farther and farther away from 512. The beat frequency will increase. However, if the starting frequency of the unknown fork is 507 and you increase its frequency, it will get closer to 512 and the beat frequency will get less, it will diminish. So by just changing the frequency of the unknown fork slightly, you can figure out for sure whether it was the higher frequency or the lower when you solved the absolute value equation. Okay, so that's beats for you, an interesting type of interference created when two sources with different frequencies ring together. Now I'd like to talk to you about one more type of interference, and for this one I'm going to show you a video. We're actually going to do this in class. This video is not in your homework schedule, so note the source and you can go watch it if you want. But remember the ripple tank that we used? Well, let me play you this video and I'll just do a little voiceover here. You're going to see the ripple tank that we used in class in previous lessons, only this time it's going to have two things bobbing up and down instead of the one that I showed you. So watch. This, I believe this is put out by MIT Physics, Massachusetts Institute of Technology. I could be wrong. I wasn't really paying attention in the beginning there. But these guys show you, there it is, the wave generator up here with two sources, and they can adjust, of course, the oscillation or the vibration frequency. So they're going to turn these on, and now what you see is two sources vibrating together side by side. These guys are at the same frequency, and that is not the same as what I just showed you here, where the frequencies were different. So we're talking about a different scenario here. Keep that in mind. Let's go back to the video and play it a little bit more. The waves from one of the sources spread out, and so do the waves from the other source, and they overlap. Now what's going to happen when they overlap? Let's pause the video and go think about this for a minute. Your textbook shows a good example. They do it using sound waves. They ask you to imagine speakers and therefore sound waves, not to be confused with the wave generator and water waves. Same idea, different kind of waves. That's okay, we can deal with that. The waves spread out. These are the gray waves from this speaker. These are the blue waves from this speaker. They show you compression and rarefactions, and they're spreading out and they're overlapping. Now, then they get into this complicated set of lines over here. What's going on? Well, let's go back to the video and watch and see if we can't make sense of this. So here we go, back to the video. Now they turn out the lights, and that's because they're going to project this up onto a screen in the dark. Now there we go. You can see what's happening. They're increasing the frequency, and you can start to see that the spaces between any joining waves is getting less and less. We know that that makes sense. As you increase frequency, wavelength declines. But that's not really what I want you to look at. What I want you to look at and notice are these strange lines that are starting to form and spread out. I'll play it some more, and you can watch what happens. The frequency is still increasing, and now you can see it really well. There's sort of these regions that are spreading out almost like the spokes of a bicycle. As the frequency goes up, the spacings get smaller and smaller, and the number of lines starts to increase. There are more lines here than there were before. Count them. Rewind the video if you have to. They form a definite pattern as well, which means if the pattern is definite and it's symmetric, then there's always some sort of link between where you are on one of these lines and how far you are from one source to another, and of course, what the frequency is, because after all, the frequency is what's changing here and changing the pattern. We have a name for this kind of interference. We call it two-point interference because there are 2 points, and it's usually done when both of the points are at the same frequency, not like the tuning forks, which were at different frequency. When this happens, you end up with you can actually figure out a mathematical relationship between the measurement of the size of the lines in the pattern and the wavelength of the waves. And this is actually something you'll learn in grade 12 when you take the grade 12 course. And we use this to do all sorts of neat stuff like measure the wavelength of light, believe it or not. Anyhow, going back to what we had here, now I hope you can see what these lines were all about. They have a name. They're called nodal lines, and some of them are called antinodal lines. Let's examine. The dashed ones are the antinodal lines. They are right down the middle. If you think about it, at any point on the antinodal line, let's just try to imagine, at any point, waves have traveled from one source and the other source, and they have met. They've traveled the same distance, therefore they are in the same phase, and therefore what we get is known as constructive interference. However, on a nodal line, as the name suggests, you remember nodes, we talked about them when we learned about standing waves. These are regions of destructive interference. Why do they happen? Well, very simply, when you're on a nodal line, you can actually see that some of the waves have they have a closer distance, they don't have to travel as far as the other waves. This point is closer to this speaker and farther from that speaker, which means the waves have traveled different distances, which means they are in a different phase. In fact, they are in opposite phase, so they interfere destructively. That's what those lines were that were spreading out in the video. In your course pack, on page 10, CP10, you'll see a diagram like this. It shows 2 point sources with waves spreading out. Here's a dark solid circle, followed by a dashed circle, followed by a dark circle again. And if you guessed that these represent either compressions and rarefactions or crests and troughs, then you're correct. Crests and troughs spreading out, same thing here. Crests and dashed lines, maybe those are troughs, and crests and so on. As they spread out, eventually they meet. When a crest from one source, for example this crest over here, meets a crest from another source, maybe this crest here, they interfere constructively and you get this. But when a crest from one source meets a trough, the dashed line from this source, you get destructive interference. And this is what your course pack has started to fill in for you. They've put little X's where the crests of one wave source and the troughs of another are overlapping. And you see they follow a definite pattern, like we pointed out earlier. Of course, you can probably judge that the shape of this pattern, exactly how bent the line is going to depend on how close the waves are to one another. That's why the pattern depends on the wavelength. And so what you're going to see in grade 12 is we're going to analyze this pattern to figure out the wavelength of the waves coming from the sources. And the cool thing in grade 12 is that we don't always use water waves, we actually use light waves. And in doing so, we can measure the wavelength of light, which is probably, I think I can safely say, the tiniest thing you're ever going to measure in high school. Even if you're looking at cells under a microscope, I still don't think they're going to be as small as the wavelength of light. So that's kind of cool that in physics you're going to get to do that. That's why you got to take the grade 12 course. Anyhow, just to finish up here, if you keep following what's going on here, you're going to see a little while later, here's another instance where crests are meeting troughs, crests meeting troughs, And what do you notice? They're following along a similar pattern. This is a second nodal line. So there's a whole bunch of nodal lines. In between them are antinodal lines, and the pattern helps us find the wavelength. And that, in a nutshell, is two-point interference. The cool thing that we're going to do in grade 11 when you come in tomorrow after this video, we're going to set up the two-point interference pattern with speakers. And so we're not going to do the water version of this. We're going to do the audio version of this, the sound wave version. And I'm going to set up these two speakers and ask each of you to walk through the room. And I want you to predict, what are you going to hear when you walk through regions with constructive interference and destructive interference? What would that sound like? Something to think about. Anyway, thanks for watching. I hope you guys start studying for the test. This is the last lesson in the unit, so you definitely want to get ready for that. Remember to review all of your notes. You might want to review all of the videos, check your homework questions, and bring any things you're not sure of, bring questions into class so that on the review day we can discuss together. All right, have a great day. Talk to you guys later. Bye now.